Welcome to part 4 on our multi-part series on general relativity. In this video, we're going to cover the Einstein Field Equations, not E equals mc squared. These are the ones we use to determine spacetime curvature from mass energy density. In classic Einstein style, we're going to explore this with a thought experiment. We'll cover geodesics, which are the equivalent of a straight line in curved space. We'll cover the equivalence principle, which is the indistinguishableness of free fall from inertial movement. We'll see second derivatives in 4D spacetime, Riemann and Ricci curvatures, and finally, we'll conclude with Einstein's vacuum equation. Enjoy. Ben,
Hello, buddy.
new day, new physics.
I know, right? Definitely. Not a long string leading into late hours in the evening or whatever terrible filming conditions we end up with. Today's not too bad.
No.
Yeah. So, last time, viewers and Rob, I left you guys with filling out basically the pure mathematics of the pieces of differential geometry that we're going to care about, right? The idea of how, for this part, how vectors are going to transform, the use of tensor to change basis from one coordinate system to another, some fun discussions about the idea of co and contravariant when combined to make sure that vectors stay the same regardless of how you look at them. You know what? Digression is what people are on YouTube for. It's fine.
Okay.
Yeah, so this is the summary of everything that we covered in the last topic, where we ended on the Christoffel symbols of the second kind. And they have so many twiddles and diddles that the awful part is well earned. But this time, it's finally time to stop talking about simple mathematics. And we get to find ourselves back in the world of physics. How do we take all of these tools that we've learned about? And how do we make it into something that lets us predict how reality behaves? Now, let's go with the central theme here. What we're ultimately working towards is saying that, is connecting that there is some function of local space-time curvature, and that is going to be equivalent to some measure of the mass and stuff that's there. So function of local space-time curvature is going to tell me something about the matter energy density in the universe. And this is what we will call the Einstein equation. It's the core piece of Einstein's general relativity that drives the whole mechanism forward. So in the same way that Maxwell's equations, let us derive the behavior of any charged particle if I know the field, how it's going to move and accelerate throughout space. Deterministically, the Einstein equation, this thing here, once we actually figure out what it looks like, is going to let us predict how do large-scale bodies behave. So we're going to break this up to try and derive it all in one go is a little bit daunting. So what we're going to do is we're going to break it up. So first we're going to work on is the left-hand side. We want to build up some measure of what local space-time curvature looks like, both our ability to detect it and then what function we will have to have for our left-hand side of this equation. All right. So a important point, what we've talked about before in the last lecture, we talked a lot about world lines and how they flow through space-time. An important point here is that if I know, say, the world line of a particular object through space-time, this line here, no matter what the dimension of the space is not, well, I guess in 4D spacetime, is not enough for us to be able to determine what the curvature of the space-time this guy is flowing through, right? Because it could look like, the space-time around could look like just a half pipe, just like a half pipe pointing up. But it could also,
I mean, the participant could actually be choosing this direction anyways, right?
right. Oh, if we just know the direction that, this thing goes, it could be if it were the half pipe, a world line going the opposite direction would follow the green line, or
Make that bigger. I can barely see the blue.
there we go. Sorry, would follow the green line, or it could be that the red line should follow the blue line, right? Those would be different space-time curvatures that match the information given to me in the white line. So if I follow the world line, how one particle travels through space and time over some amount of time, right? And track that, I don't have enough information to fully determine the curvature of the space-time it's flowing through. So how are we going to be able to do this? Well, I need, as I just kind of drew out, if I have maybe two curves, right? Because if I have the white line and knowing whether this red line or this red line is what matters, I can then determine for you what the curvature is, at least at the point where the red and the white line exist, or intersect, not exist, where they intersect. And then, I might get that information for the whole space-time, but we'll get there. So if I have information on the relative motion of multiple particles, then I will be able to make a prediction about what curvature is in my space-time, right? To kind of understand how this looks, what we can do is we can look at what's called tidal forces. So to get a picture of this, let's jump to the Newtonian perspective real quick. What's going to happen if I have, so in the Newtonian perspective, I'm going to have some mass that creates the gravitational force around a gravitational potential field, and any masses that are in that field will deviate from straight lines based on the gravitational force from the outside object they experience. So here's the thought experiment to consider. Let us say we've got two observers. One, we've got a little cat friend and a bunch of balls, and he's in a spaceship just out in free space, completely alone, completely isolated from any other test map. And you have another buddy here, but in this case, let's make sure you're blue. They are just outside the Earth. As the classic YouTube video goes, this is the Earth. Right? So as time evolves, what's going to happen to the balls around these two observers, two little friendly happy kitties? Simple. As time evolves, the balls around the free-falling observer in space, since they experience no external force, according to Newtonian physics, they won't move. They're already stationary, so everything stays in this nice, perfect circle that's arranged.
So they'll eventually just clump onto the cat.
Yes.
Okay.
For masses this small, it takes a very long time to do that. But over, an hour, you won't really be able to even measure the deflection from such small test masses, right? However, the ring of balls around the falling towards the center of the Earth, what they feel, right? We know that the gravitational forces, let me use magenta, right? The gravitational forces point radially in towards the source of the mass. So they will point radially towards the center of the Earth, which means we have this. All right. The direction of the forces they feel are along like this, right? What's interesting as well is we also know that gravity depends on the distance from the center of source of gravity, 1 over that distance squared. What that means is that objects that are radially closer will accelerate faster than objects that are farther away with a greater r, right? So what that means is that over time, labeled magenta, is that this ball, as the frame of reference moves down, relatively, it will look like that this ball moves here. Whereas the ball straight up here will lag behind and seem like it's getting further away from the observer. Balls that are roughly on the same plane.
So the cat's falling as well, and he's the observer?
Yes. So
Okay.
the cat is falling with the balls.
Okay.
Right. Just like how the cat here is just floating with the balls. The cat here is in the reference frame of the center of mass of these balls. Right. Balls that are relatively on the same plane. So if I had a ball here, right, they obviously are going to have the same R, but this force pulls them together. So it would effectively look like, delete this guy, that they are coming closer together. And same thing up here, although these guys are lagging behind, so they'll end up kind of like here. So if I have a spherically oriented set of free masses and the influence of one big gravitational mass, what we see is a stretching of the matter along the radial direction, pointing towards the source of gravity, and a squishing of that matter along all the perpendicular directions, right?
Mm-hmm.
Now, we're all familiar actually with how this works, because the reason it's called tidal forces is this is exactly the phenomena that creates tides, because the moon affects the oceans, the water around our Earth, like the free floating balls. It causes a bulge to point along the axis pointing towards the moon, and it shrinks the oceans in all directions perpendicular to that. So what we know is that this phenomena causes this tidal force. So we know that the distance between these balls as time goes on is going to be affected by the gravitational curvature, right? And the way that we'll show that, we'll show that in the math real quick. So mathematically, the way the Newtonian picture works is to say that I give you some distribution of the mass density. So basically, I specify for you at this point in space-time, there's this, or at this point in space, there's this much mass. At this point in space, there's this much mass. At this point in space, there's this much mass, right? And from that, what I'll do is I will create a potential, which is simply looking at, okay, at some certain point, I look at the potential influence of constant times all, actually, let me make that mu just for density, all of that space-time, and then divide it by 1 over the distance from where I'm comparing to where the mass is, the magnitude of that. And I just integrate that whole thing, right, in 3 space. From that gravitational potential, what I can tell you is that if I'm interested in, say, x prime, which is the position of mass, that I can tell you that the way this thing will accelerate, how its second derivative with respect to time works, is going to be related. Drawn the wrong thing there. Is going to be related to this potential via its differentiation in the right direction. So here, to line up with the labels we've been using, we'll do delta ij. Basically, I look at the derivative of the derivative of this scalar function in each of the spatial directions I'm considering, and that gives me a connection to what is the any test mass x primes acceleration at that point, right? At the point xk. That make sense?
Yeah.
Okay. So this is effectively F equals ma, where your acceleration is equal to here the gravitational force divided by its test mass. That's what this side is. This is your acceleration vector, and this corresponds to F divided by m, basically. Okay, divided by the mass itself. All right. So in order to get to the curvature of this guy, what we're going to do is we are going to look at two balls. So the first one we've got at position x prime. And now we're going to introduce chi, which just tells me which is the separation between any two balls. Okay? So I'm going to have two balls in space, and they're experiencing gravity based on this potential phi. And so the second ball's position would be at x prime plus chi prime. Okay? Right, the separation. You know what? Yeah.
Did you just put an X and a chi in the same?
It's not my fault. This is what Harda loves to do. I'm going to say, actually, that's so much to write. Let's call it this.
I might have missed. Is there another chi then?
No.
Okay.
No.
All right.
So the separation, let's call it S prime, just to make our lives easier.
Okay.
Since my handwriting is atrocious. All right. So since this is the motion of the second ball, what I know is that it will undergo F equals ma as well, based on the second differentiation of its position, which is x prime plus s prime, with respect to time squared. And that's going to be equal to negative ij, the partial differentiation of the potential at point xk plus sk divided by, or with respect to the xj. Boop. Like that boy. Right? So basically I can say, oh, okay, if ball 2 is at, a point x plus s, then it will experience some acceleration, some second time derivative change based on that potential, right? Same form as over here. Okay. Now, I'm going to feel the shame in my physicist-y heart, as what I do is I expand. Nope. There we go. Is I will do a Taylor expansion of that partial differentiation of this guy. And I'll do it with respect to the separation vector. And so that'll give me, okay, first order, just the constant, which is just the partial differentiation of this at the point where the original particle is, or the first particle is, plus a partial differentiation now of that same object and now multiplied by chi s k plus higher order terms. Now what we're going to do is that we are going to simply have our amount of time be so small that the only thing that will matter is the first two terms.
Okay. What's going on with the superscripts here? So you have I and j.
Yeah, this should be I, and I as well. Excuse me.
Okay. And what happened to our K?
K is going to be the coordinate where the second ball is,
Oh, okay.
right? So I'm looking at, I've got if the first and second ball overlap with each other, right, then xi and xk are the same thing, but here they don't, so I've got some like separation. So
Okay.
I've got to take a differentiation with respect to that.
All right.
And basically what I can do...
So we're each I, J, and K are separate balls.
Yeah.
Okay.
An important point, since the differentiation is a linear object, I can replace this with, instead of, looking at differentiation of both of them, I can say that this must be equal to the sum of the differentiation of both objects. So d squared x xi dt squared plus d squared s dt squared. So if I subtract this equation and this equation, right, because of this expansion to first order, I can isolate what this guy is, right? And so I can say, okay, the acceleration that the separation vector, distance between the two balls, will experience is going to be related to the second order partial derivatives of my potential, of my gravitational potential. Now, if you remember from basic from calculus, and eventually this extends to differential geometry, this to multiple spaces, this is the thing that is directly related to a measure of your curve, right? If I know, some function, its curvature is related to the second derivative of that function with respect to its variables, right? Now, when I go to multiple dimensions, I don't just have one variable. I have two that I need to consider. So I look at the second partial differentials with respect to any possible combination of its variables. For us, it's going to be, for spacetime, eventually it's going to be 4 variables. But Newtonian physics, in regular 3D, it would be 3 variables that I would have to consider all the combinations of partial differentiations with respect to. So I would get a 3x3 matrix, right, just like I often do in Newtonian mechanics. With GR, what we'll eventually find is this is a 4x4, right? And what's fun is this is actually directly related to the field equations that we use to find what the field should be, right? The most classic Newtonian equation is that the Laplacian of the field, as it's called, which translates to the second partial differentiations, is equal to 4 pi, the gravitational constant, times your mass distribution that was given to you at the beginning.
That's a familiar term.
Yeah. Well, the mass distribution, mass density, that's the thing that I defined at the very beginning. This guy.
No, I mean the 4 pi g.
Oh, yeah. That factor is common. I thought you were saying that thing. All right. So this is how we go about in classical Newtonian physics. How do we get a notion of the curvature? And obviously from that, the curvature of a thing. In Newtonian physics, it's the curvature of the gravitational potential. And from that, I'm able to deduce, discover, and realize, oh, this is really important for the entire dynamics of everything I want to do as far as gravity is related. So just as we've been doing, we don't invent the wheel. We just look at how does stuff that we knew worked in one paradigm of looking at things, how does that generalize to the new paradigm that we're trying to analyze everything with. So in GR, it's how do I take this equation, this measure of curvature, and turn it into something that I can do in 4D curved spacetime. Okay, so in order to do that, I'm going to have to introduce to you a new concept, specifically the idea of a geodesic.
Ooh.
Yeah. So put pretty simply, a geodesic defines for you what is the path between 2 points in this any space you're considering. What is the path that minimizes the distance between them? Right.
The shortest path.
Yeah, the shortest path possible. For a flat space-time, right? Even in Einstein Minkowski space, what I know is that straight lines are the shortest distance. So what's a way to mathematically characterize that? Well, if this is my world line, right, and I've got event A and B, and I know they're connected by this, and I know intuitionally that it should be a straight line in flat space, and I can show that. An object that I know is associated with this is the tangent lines, or the tangent vectors at each point. And what I notice if I look at the tangent vector, let me make sure that's nice and big for you, is that when I look at the tangent vector here versus at another point here, right? So let's call that it's here, that's its 4 velocity u at a point x alpha. This is x alpha. And then another point x alpha prime. Primes are just great. It's just another point later on. I know that this guy, x alpha prime, is the same vector. They equal each other, right? If I look at these two things, the magnitude of my 4 velocity, as we discussed before, is always going to be 1. And the angle hasn't changed in this space. The angle with the basis vectors hasn't changed at all because it's nice near Euclidean, like rectangular space. Everything's all orthonormal. From a condition, so from here, I can come up with a pretty easy condition, and that is that the covariant derivative that we talked about last time along that 4 velocity vector. So what is the differentiation of the vector as I move along the direction that it defines? That is equal to 0, right? Because when we defined the covariant derivative, we took, it's a derivative at a later point, subtracted it from it at a starting point, and then looked at the difference, right?
Right.
But if it never changes along that path, that subtraction will always be 0 because they're the same thing, right? A minus A is 0. So this is a condition. We know we have found a geodesic as long as the covariant derivative of the 4 velocity along that path that connects 2 points in space-time, is 0. Okay? So now, how do we translate that into an equation, a picture, just like kind of basically like an F equals ma kind of equation over here? The short answer, I'm going to skip some of the math because I can do that. Effectively, what you do is you take this condition, plug it into the Lagrangian for gravitation, which is its own set of mechanics and is messy without being terribly illuminating in this context. So we're going to skip it.
Cool.
And it gives me this condition, which is that if I'm looking at the acceleration that I experience along some world line x alpha, right, which is a function of my proper time, right, it's acceleration that it feels, not t, but tau for proper time, is customary, is going to be equal to negative a Christoffel symbol of the second kind, beta gamma, and the basically 4 velocities, u beta and gamma. So like in order to fill out the matrix multiplication, it's still the same. Obviously, the components of this and the components of this will match. It's just I'm going to need to match them up with different components of this. This is also equivalent to same thing, but the total differential of your world line with respect to proper time and world line with respect to proper time, just in where I'm matching different components in order to get the right thing. So with this, what we can talk about now that we've defined what our geodesic is. So you want to figure out what the geodesic is in your space, then you solve this partial differential equation as a function. So the solution will be some world line that solves this thing, that makes the left side equal to the right side.
Okay.
Okay. Okay. So this allows us to summarize, right, the way that we look at how GR functions, right? In Newtonian physics, it was I've got some mass that produces gravitational fields, and I'm interested in some outside mass. How will that move through it, right? Here, what I'll have is particles will follow geodesics in the space-time, and those geodesics are defined by the curvature created by the mass you place in your space-time. That's not the one you're following. But here's an important point, is that and an interesting experience is that as long as you are following a geodesic, you will experience the feeling of weightlessness. And this is the entirely like counterintuitive thing. Like if I
because you're not resisting.
Right, when I jump off a building,
Right.
I'm following now the geodesic of the Earth's space-time curvature around me. And so I feel weightlessness. Just like how the observer out in space, the balls around them, they are weightless because they are following the geodesics of the local space-time curvature.
Now, can you affect your own geodesic? Or can you, like if you're super massive, do you also affect the geodesic as you're falling?
In the same way that a electron in an empty universe doesn't move. Because even though there's an E field around it, it doesn't interact with the E field that it produces.
So we're only counting every other object, not the object in question.
Basically, if you're from physics, you say, I want to look at how does this one object move. Everything else in the universe will be a source of gravitational force, curvature, etc. And then based on how everything else affects this particle, then I'll watch how it moves. But what I never do is go, okay, how does this particle affect its own movement? It doesn't. If it's the only thing in the universe, a particle just stays still.
Okay, but to be fair, we are talking about situations where there's more than one object in the universe.
Yeah, we have to.
Okay.
Yeah, there has to be some source of curvature that's present.
Okay.
In order for there to be anything interesting.
Okay. Now, does this function naturally evolve with the movement of the other objects?
Yeah. If you're yes.
Okay.
So basically, your Christoffel symbol is going to be a function of space-time. So the curvature you look at is only at that particular moment in space and at that particular time. So that will encode how the rest of the objects in your universe are moving through space and time.
Okay.
Right.
Because I mean, we've got n body here.
Yeah. Right. So computationally figuring out what your Christoffel symbol should be, can be difficult, and in practice almost always is. But
Okay.
the mathematics of what you do, regardless of the number of bodies you have to work with, is still the same. It's just figure out that Christoffel symbol for all the universe, aside from the one thing I want to pay attention to.
Okay.
Right.
Sounds good.
Yep. And so this is actually contained in, here we go, Einstein's equivalence principle. There we go. All right, which is that experiments in a sufficiently small, freely falling laboratory over a sufficiently short time give results that are indistinguishable from those of the same experiments in an inertial frame in empty space. Right? So if I take my balls and jump off the building and fall, what I'll see is the same as empty space. I'll see the same picture, but it has to be over a short enough time in order to experience that. Make sense? So this is as anyone who's watched some more direct example. It's Einstein realizing that if you're falling, right, jumping off a building, you are experiencing the same thing that someone floating out in space would. That weightless experience are equivalents. The physics that you will measure in those two reference frames are indistinguishable, given the right constraints on the distance and the time.
And I think it's kind of key. It's sufficiently small. Like this isn't generally. This is.
Yeah. So it's basically saying that the physics that I see is going to be valid in a flat space time. So if I allow myself to evolve too long, the tangent space that I was in before changes.
Is no longer relevant.
Right.
Right.
So how much your results deviate from that is something that you'll eventually be able to account for with the proper amount of differential geometry and understanding general relativity deeper. But in essence, to get the truly equivalent, we have to say, okay, I stay in the same tangent space. And so sufficiently small is given meaning by that, even though, in calculus, how small does it need to be? It's like, it's a little fuzzy.
Right. Infinitesimally.
Right.
Yeah.
An infinitesimal is a hard thing to grip. It's not quite zero, but it depends on how you want to do it. There's fun math systems where you define the inverse of infinity as an infinitesimal. That's its own little thing. It's the hyperreal numbers. How I'm not sure if that directly relates to the observations we see in physics, but it's a thing. It's a math system that's out there. So like defining what a infinitesimal thing is an important thing. Yeah, so things follow geodesics unless there's an acceleration that causes them to deviate from that that path. Which, you might think, like, obviously, if I'm falling down from a building, it really doesn't seem like I'm the one that's not accelerating in that case. And the answer is, well, yeah, because of curved space-time, in order to make it so that I'm standing still, I have to add some kind of acceleration to balance out, the effect of the curvature inherent to the space that I'm in. Right?
Yeah, you're experiencing a space-time induced or curvature induced acceleration.
Right. So the question is, obviously I got some geodesic, and I've been talking about that the Christoffel symbol of the second kind, this guy here, is related to curvature and captures it. But how do I go about actually showing that? Well, simple. I do what I did before, and I look to Newtonian physics, and I figure out how do I generalize this situation to general relativity. And the situation was simply studying how does this vector here, the separation between two different balls following their own geodesics and space-time, how does the distance between them evolve as a function of that evolution, right? As a function of basically their proper time as they would measure. And so the basic picture.
And just a little point that I think is kind of interesting. What you're describing is there are actually methods that we can determine our own curvature. So even though curvature is 4D or whatever, and we're 3D with an extra dimension, we can still measure
Yeah.
the curvature of the space we're in.
We wouldn't be able to do anything if we couldn't.
Yeah.
Right. So let's, nope, come on. You know this is this is not my finger. So let's say we've got 2 geodesics. Okay. Let's say now I've got the observer and their proper time parameterizes this path, right? And so he's got some 4 velocity u that points along tangent to this vector. And then there's some separation at a point, which we'll call S, right? The question is, how does S change, the separation change as a function of my spacetime? So I basically want to recreate this formula, but in orthogeometry. So what I need to do is be able to isolate a second order. Basically, what I want to do is find a formula for this guy, right? Which I will define as some vector W. Okay. So the second derivative, the second partial derivative following along the 4 velocity of the observer. Right? What does the observer see happening as I move along in my spacetime? Okay. Well, unfortunately, we can, since this is, like space, I can do just one on top of the other. First, I will define my v function, which is my v, which is just the covariant derivative of s. I should be drawing little arrows on s, but I'm going to drop that for the sake of everyone's survival. So write this out. The form of this, right, was the 4 velocity times the full derivative of s in a particular direction. If I'm looking now instead of at the full vector and instead my components, right? Because in GR, to make everything easy, I'm going to just pay attention to the components, and so I can change the index to figure out what each one should be, right? All right. So a more filled out formula for that was the derivative of s with respect to proper time plus a contribution from the Christoffel symbol, u beta, u gamma, right? And then what I can do is say, oh, well, okay, w, the components of w, since I know this is equal to v, are just going to be the covariant derivative in the direction of my 4 velocity of v, its components, which follows a very similar formula, right? The derivative of v with respect to proper time plus the contribution from the Stoffel symbol, which I'll call delta and gamma here. Delta, gamma. Hey, with it zoomed in, it actually is a little bit easier to differentiate. Nice. So, how do I survive this? Well, I won't go through the entire thing, but obviously I take the formula for this, plug it into here, carry out this differentiation with respect to tau, the proper time. Let me use a different color. Plug it in here, carry out this differentiation. And then what I also want to do is set up a similar equation. And that this will be a similar equation that lets me describe I do. Oh, right. Okay, excuse me. Before I jump too much. What I know is that both of these functions are geodesics. So I can use, where did I put it?
Which two functions?
Both the world line, that I'll label as x alpha, and the world line x alpha plus s alpha. These are both geodesics.
Okay.
Which means my formula for what they look like, right, is going to be this guy here. Well, without the A. Right, this guy here. So what I can do, right, is I have this formula for the blue. I have a formula in terms of Christoffel symbols for x alpha with respect to tau. I also have a formula for the other geodesic, which is x alpha plus s alpha with respect to tau squared. And just like how in Newtonian physics, I could linearly separate out the x and the s, I can do the same thing here. And then with a Taylor expansion of the Christoffel symbol with respect to the coordinate of s, I can come up with a thing that describes e squared s alpha d tau squared as some function of Christoffel symbols. So, and the appropriate four vectors so that the indices match up. I won't do that because that is painful, and there's a lot of indices to follow through on and everything else. But once I plug everything in, what it ultimately lets me do is say, okay, it ultimately lets me say that the formula I was after, which was the components of the second covariant derivative along the geodesic that I'm observing of my separation vector, components alpha, are equal to a constant that I will call r, which has these little projections. That is a function of my four velocity, my separation vector, and my four velocity again, where r is defined in terms of Christoffel symbols and its derivatives. Not a minus sign there. So this guy, all the algebra works out that it is the partial differentiation of this Christoffel symbol with respect to the coordinate gamma minus differentiation. This guy, beta gamma, differentiated x delta plus Christoffel alpha gamma epsilon Christoffel gamma beta delta minus alpha, delta, epsilon, beta. So here we go. This is in differential geometry what is known as the Riemann curvature. So it's our first notion of a measure of local space-time curvature. And with this, I have the tools necessary to define for you the first, the easiest, and the simplest Einstein equation. Specifically, what I do is I define a new curvature, the Ricci curvature, which is r lowercase alpha beta. I know it's annoying, but it's simply the Riemannian curvature where the upper index is summed along the second lower index, like that. Seeing how there's gamma in both upstairs, downstairs means you sum it out, right? You contract it out. And the vacuum, I know, right? So bad at spelling. The vacuum Einstein equation is simply this. R alpha beta is equal 0. That's it.
Okay, so what is that saying down there?
So remember how way at the very beginning is that I talked about how the fundamental equation of general relativity is going to be that there's some function that measures local space-time curvature, and that local space-time curvature is going to equal some other function that measures a matter energy density present in your universe. Right? That is what an Einstein equation is. Okay. And our first example is, okay, the first Einstein equation. It's the vacuum Einstein equation. It's the simplest one. And it's saying this measure of curvature, which is your Ricci curvature, which is related to Riemannian curvature through a contraction.
Okay.
That measure of space-time curvature must be what you see when there is no energy density present in the space that you're looking at.
Okay. All right, so what we're saying is that empty space is not curved.
No. Not at all.
We're not?
No, what I'm saying is that empty space is curved based on this Ricci curvature, so that I can have some amount of curvature in my space-time, even if the space that I'm considering has no charges within it. So what this will come to is actually
Charges or masses?
Well, this will be masses.
Okay.
Right, because this is gravity, so we're interested in mass. The mass energy density is what causes curvature in space-time.
Right.
But even if you don't have any mass in the space-time you're interested in, and that is a caveat, I'll get there, you can still potentially have some curvature that shows up.
Well, I know we haven't gotten into vacuum energy yet. Like we're skipping that.
We don't have to. GR doesn't care about vacuum energy. That's an entirely quantum mechanical phenomenon.
The cosmological constant?
Vacuum energy and dark energy are different things.
Okay.
Yeah, it's great.
Okay.
So what we will, and I'll give away the punchline here. What we'll use this vacuum energy equation to show is we'll derive the Schwarzchild metric from this, which is the origin of your Schwarzchild radius and the first prediction, the idea that a black hole pops up in space-time, that there's something fundamentally that happens if the right curvature exists in your space-time that changes how physics works. GR, and this is, GR's quickest and perhaps most profound prediction. I'll give it away a little bit here. I guess we'll re-summarize the thing. So this vacuum equation kind of plays the same role as if you have, as like with Maxwell's, right? We look back at what happened in classical physics, and there should at least be analogs. And just because I don't have any source of charge or current in the space that I'm considering doesn't mean that I won't have E and B fields present in it. Think about empty space. I can have absolutely empty space, no sources of charge or moving charge anywhere, but I can still have photons moving through it.
Oh, okay. So it's not truly empty. Right?
No. It's empty of the things that would cause E and B field, but it's not empty of E and B
Okay,
field.
I see the distinction you're making.
Exactly.
Here. Okay, all right.
Right? You can still have those things. So we can still have curvature.
So and so we're jumping 3 lectures ahead now. It's basically where you're going with this is that a gravity wave could exist and there could be a curvature.
Exactly.
Even though there's no mass.
The two solutions to this are the Schwarzchild metric and gravitational waves.
Okay.
Right? In the same way, effectively, and I'll reiterate this for the next lecture, in the same way that with the right way you define the space that you're interested in, the solutions to the vacuum equation are a single point particle and and electromagnetic waves. So that'll be next time. Tune in.
Cool.
Yeah, it's good stuff.
Yeah, man.